All right, let's look at programming by datasheet. The most bare metal way to program a microcontroller, almost that we can possibly get. No assembler, no compiler, no nothing. All we need is the datasheet and the tool to write our code in a text file, and then finally the way to upload that code, those bytes, to our program flash. First, let's review our architecture for this. AT-Tiny85 has an AVR architecture, and we're remembering that we have a program flash memory. Program counter is the most important thing in a CPU. It tells us what is the next instruction. That is the address into flash, the data at that location, stored in the instruction register, and then decoded to get our rest of our CPU to do what we wish. Down here we have data SRAM. That's our variables and such. We will not be using that today. And then 32 general purpose registers. Each of these registers are 8 bits wide. All right, so next up, let's look at the memories that we do have available. Data memory and program memory space. We're doing the 85 at Tiny85, so this is 8K bytes. This is really KB bytes, 8192 bytes. And we see here that it is organized as 4096 by 16 bits. This means that this is 2 bytes wide. 4096 times 2, of course, 2 bytes in a 16-bit word. That's our 8K. But really, it's 4096 instructions. Most of these instructions are 16 bits wide. There's a few instructions that are actually 32 bits wide. All right, let's scroll down. Let's look at our memory map. Memory map tells us the addresses and what is located at that address. Our program memory just has program memory. It starts at address hex 0, goes all the way up to hex 0FFF, which is 24095. There we go. Our data memory shows up in different places. It says that the register file, the I/O memory, and the data RAM all show up in this address space. That's something that we'll talk about later. We scroll down, we see that 0 to 1F is our 32 registers. 64 I/O registers, that's our registers that we use for peripherals to configure things. 20 to 5F, 64 of those, and then our first variable, true variable that we have in data is 60. We're not using that, but it's organized as 512 bytes, and those are 8-bit entities. One thing to notice, note that when we are using RAM, that it takes 2 cycles to access that. So if we want to go fast, we should avoid hitting up RAM as much as we can, or especially in loops where we're doing this often. And what happens after we come out of reset? During reset, all registers are set to their initial values. Program starts execution from the reset vector. Reset vector is just a fancy name for address. It starts at that address. We say it's vectored there. It's like a direction. The instruction placed at that address must be an R jump, a relative jump. But if we never enable interrupts, we don't need to worry about that. Our first instruction does not actually need to be an R jump. Nearly all of our programs after this, after a few examples, we will use an R jump, and you'll see why. All right, so we want to see what is that reset vector. What is that reset vector? Well, what we're going to do is we're going to go and look at our interrupt vectors. This is section 9 in the data sheet. And here's our interrupt vectors. Our very first interrupt vector is the reset vector. Shows up at flash address 0. If we have other interrupts enabled, let's say if the ADC interrupt fires, our program counter will be loaded with hex 08. And then we will execute the instruction in Flash at that address. So that's why we need to jump out of this table. So our very first 15 entries in our Flash are these reset vectors. That's why each one of these is usually a relative jump. For that, we're not going to turn anything on. So our first instruction, we're going to start at the reset vector and just continue. We won't hit any of these because we won't turn them on. All right, what are we going to do? I'm going to flip over to a text editor. Look at this. So we're gonna go. What is our first task to do? First thing. These are comments here. Our very first thing to do is set port B pin 0 to and output. That means we need to set DDRB bit 0 to a 1. How do we do this? Well, first of all, we need to say what is an instruction that can set a bit. Well, I've already looked at these. If we look through the instruction set manual, this gives us all of the AVR, but we can also go in the datasheet here, go all the way down to instruction set summary, page 202, section 24. These are all the instructions that our @tiny85 can do. All right, so if we look around here, we say bit and bit set instructions, and I'm going to zoom in here. IO register is what we want. SBI set bit in IO register. We have two arguments, P and B. Port and B, this sets that bit to a 1. We can also set a bit to a 0. And what this is doing, go up here. These are the flags and then the number of cycles. If we go down here again, it does not change any of our status register bits, and each of these takes 2 clock cycles to completely finish. You might think of it as it reads it, it writes it back. We'll get to that, but it's one instruction. How do we get to this? Well, we're going to encode SBI in an instruction. So let's look for SBI. Let's jump there, 31. Okay, so here is the instruction set manual, SBI set bit and IO register. It operates on the lower 32 IO registers, 0 to 31. It's okay. We'll see if that's relevant for us. Here's a restatement of what it does. A is our address, 0 to 31. B, this is 0 to 7. This is the bit number. We want 0 for our B. Program counter just steps along to the next instruction. Syntax, SBI. We're not going to write an assembly. What we really need is this 16-bit opcode. Well, I'm going to leave this 16-bit opcode down here, pull up my editor. There we go. So this would be SBI, and then what register is this? Well, I know it's going to be bit 0, but I need to find DDRB. Okay, DDRB, what is it? Let's go look up in our datasheet. So here we go to the datasheet. We're going to go to the register summary, section 23. And we see all of our registers. You see some timer registers, a bunch of timer registers. The status register is very special to us. Let's see here. We could just have searched for this. But here's port B. We'll need that here in a minute. Here's DDRB. DDRB is at IO register number hex 17. All right, so it's hex 17, SBI 0x17. we need to encode this into a instruction. Let's go back to our instruction set manual, SBI. SBI, the first two are 1001, 1010. This is 8, 9, and then this is 10, or hex A. So this would be 9A, and then we need the final bits. It's 1, 2, 3, 4 bits of A. The fifth bit of A, remember A is 5 bits, and then 3 bits to describe our 0 through 7. Well, let's do some scratch here. So A is a hex 17. 17 is 0001, and then 0111. Okay. Well, that is actually, we need 5 of those bits, so it's A. We'll do this here. B is a 0. All zeros, because we're addressing bit 0. I'm going to encode this into, remember, 5 bits here. So this will be A, and then A, B, 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 which would be starting from this one, 1, 0, 1, 1, 1. So let's do that. 1, 0, 1, 1, 1, and then 0, 0, 0. That's the last byte, or last 8 bits, which is, we'll encode this, 1, 0, 1, 1 is B, and then 1, 0, 0, 0 is 8. So our very first instruction is SBI, is this word here. So I'm going to delete all of this. Our next instruction is, to set the pin high. That's it. Okay. How do we do that? Hey, that's another SBI. SBI, and this would be port B, bit 0, but we need to encode this in here. Let's see. Port B is, we need to go back to our data sheet. Port B is hex 18. Okay, hex 18. And then 0 here again. So this is another SBI instruction. It's going to start with 9A. And then this is 1, 8 is 1, 0, 0, 0. Okay, so this is that's our 5 bits of the address. 3 bits of our B, that's all zeros. If we rearrange this, we look like this. Okay. And this would be 8, 12, what was that, C? And 0. So this is 9A, C, 0. Encoding that into our opcode format. It's a little weird here, but that's just how the bits are packed together. So that's our second instruction. We only have 2 instructions so far. The final thing that we want to do is do a while 1 loop and basically not do anything. We set the pin high, we're done. What we are going to do is we're going to jump, repeat, set pin 0 high again, which means we need to jump our jump instruction. And let's go look at our rjump instruction. Go to our instruction set summary. Logical ones, branches. Here's rjump. Rjump is a relative jump. Scroll over here. K is a constant. Happens to be assigned constant. Program counter plus K plus 1. Now be careful. Remember this plus 1 here? Usually the next instruction, this one, program counter plus 1 is this. When we do our rjump, we're going to go here, that's our next one, but we want to go back. So when we're on our rjump, our next one, program counter is at this location instead of here. So we need to go back by 2. We can go back by 2 and continually set our bit high, or we can just go back to our R jump and R jump, R jump, R jump, and we're just jumping to ourself. Actually, I like that better. While one, we'll just say do nothing. Write that in C code. Delete that to self. All right, let's look up the AVR instruction set. So we're going to look for R jump. Let's go back to RJMP. R jump. R jump. Here's relative jump. Skip to that. Where's R jump? Here's relative jump. Relative jump to an address. Minus 2k plus 1 to 2k. This is a signed integer. Our opcode is 1100, which is C. And then all of these k's, we concatenate all of those together. It's a 12-bit number. Remember, we're going to go back by -1. I want the program counter, the next program counter, to be the current program counter. So I want PC to not change. That means PC needs to go to PC. That means K has to be equal to -1. If you remember how to do sign or 2's complement numbers, we have this will be F, 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 which is -1. So let's do that. C, F, F, F. And that's it. 3 instructions in this. All right, so I'm going to write this out of here. Yeah, that's okay. And then now we have this short little program called RCF to iHex. Let's just look at it really quickly. All it does is it converts our hex values into Intel hex format, which is the file format and the contents of it that our programmers like to use, including AVR dude. All right, so we have this Intel hex. Intel hex has been around for a long, long time. What's it say? 1973. All right. 1973. It's really easy format. It has records consisting of 6 fields. Everything starts with a colon. Then it has a byte count, then an address, then the type of the record, then the data, and then the final item on the line is the checksum. So when it's colored like this, colon 3 is the number of bytes, and here it is, number of data bytes, 1, 2, 3. This is the address. This is hex 0030. The record type is a 0, which is just data, and then the sum. The checksum is actually quite easy. It's if I take all of these bytes together, including that, the checksum 1e, I get 0. So to compute this, you can read Wikipedia's thing for that. All right, there's a bunch of record types, or several record types. We're going to use data, and we must have end of file, and it looks like that. All right, so we're going to skip right back to our, we read it. We're going to do hex format. Our start address is at 0. Remember, that was from our data sheet. And this allows us to have comments. We're going to read 2 characters from our line, convert those to hex, or treat them as hex, and that is byte number 1, and then byte number 2 is the second 2 characters. And we append these to the file little endin first, and we'll see how that works out. And compute the checksum and print these out. Not a big deal. So if I run this on my main.rcf, actually just show you this. That's the file that we just made. Okay, so RCF to iHex, main, RCF. All right, we get these 2 lines out of here. If I put this to raw.hex, and my text editor colors these 6 bytes, 6 data bytes, 1, 2, 3, well, 1, 2, 3, 4, 5, and 6. If we look, we see this is B8, 9A. But if we look at this again, let's look at our main RCF. It was 9AB8. Why are they backwards? That's because we put the little end in first. Little end in. We see our the count is 6. We have 3 words, but each word is 16 bits. All right, we can count like that. No problem. If we program that to our microcontroller, then we're just done. That's pretty cool. All right, next video, we're going to do this in assembly language using AVR sim and see that we get exactly the same result.